All right, here we go. We're going to take a look at the second derivative test, which is pretty awesome. So it's going to help us with our curve sketching here and finding the extreme, just like the first derivative test was finding those max and mins. Got another way to do it and some other cool stuff that deals with concavity here. So concavity is pretty huge. When I think of concavity, I kind of think of that girl from Orange is the New Black right there. Check out her teeth right there. She's a prisoner with bad teeth. Anybody? Anybody? Concavity? Ooh, that was a little rough. A little rough. What is it really for math? So let's check it out. Concave up just means, like I always think like of a bowl, like holding water, or a parabola. This is concave up. So it's something that I always think could hold water. It takes that shape. What's concave down? Well, it's the opposite. It would be an upside down. It can't hold water. So it happens in graphs a lot. We kind of look at the shape of it. Is it concave up or is it concave down? What causes concave up? Well, concave up is from the second derivative. It's when the second derivative of the function is positive. So when it's greater than 0, and you could probably guess this is when the second derivative is negative. It causes this concave down shape. So if I look at my picture over here, where's this thing concave up? Well, if you look at it like this, here it is. It's kind of holding water. It is concave up right until this point right here. Then what happens? It is actually concave down. So it's concave down to here. So it's only just a piece of it. Like if I continued it, it'd probably come back down. But it's just this piece is actually concave down. Then what happens? It changes concavity here. It is concave up. Holy cow. And then what happens? It is concave down. Looks like the rest of the way. That is concave down. So that you can see the concavity changing throughout. And then in there, when it changes concavity, so that's what a point of inflection is. This is the point where it changes concavity. So that's the point of inflection. So if it changes concavity, you can see a point of inflection right here. See how it goes from concave down to concave up? It even happens right here, doesn't it? There's a point of concavity, and there's one other one right there. So this case has 3 points of concavity. Boom, boom, and boom. What's causing it to change concavity, or what's happening at these things? Well, it's going from a plus to a minus. So when it's changing in there. So things we look for points of inflection, this is when the second derivative equals 0. So when I have like a little flat line or does not exist. So if I look at the slope of the tangent line, what's going on right here? They happen, well, the slope of the tangent line here is 0, slope of the tangent line here is vertical, and vertical, they don't exist. So these points of concavity can happen when the second derivative is 0. Is that always the case? Well, the second derivative is actually 0 here, isn't it? And it's also here, so it's not always going to be. We have to look for that change in concavity. Awesome. So can we put this into a friendly table? I tried to mark these little areas. So from negative infinity to 3, the second derivative was positive. I'm just going to abbreviate, say it's positive. What happened when it gave me that positive? Well, it gave me this concave up. So that's kind of cool. Then from 3 to 4, what happened? It was concave down, wasn't it? So from here to here, it's concave down. So what is my second derivative? If I knew the equation and could find it, it would be negative. And it keeps changing, doesn't it? The second derivative was positive here. And then that's from 4 to 5. And then from 5 to infinity. So you can see that what's going on. So when we've got concave up, we've got concave down. So when I go to kind of evaluate these or look for these things, I can see the change in concavity from concave up. It's going from concave up to concave down. This is going to be at 3 a point of inflection. And I can see it right there. Same thing, goes from concave down to concave up. I've got another one at 4, and concave up to concave down. So we're going to do a lot of reading these charts or these signs, and that's it. Like, that is the only new information, but it's got a ton of applications. We got a lot to do with this bad boy. So that's the key. Point of inflection changes concavity, concave up versus concave down. So what's its main application? Well, second derivative test. That's the name of the section. So what's going on here with this second derivative test? So if we look at the derivative is 0 at a point C, then some things can happen here. So the second derivative test, so if I look at this, let's say I have this function, I've got concave up. If at point C, the slope of the derivative is 0, so that would be point C, and it would be 0, wouldn't it? Because you've got this flat line. Then what's happening? Well, if it is concave up, what is that? That's going to cause a minimum point right there. So if you have concave up, or if your second derivative is positive, so this would be the second derivative is positive, oops, and it's going to be actually at C. So we can say the second derivative at C is that. It's going to be a minimum. How about the opposite of that? What if the second derivative is negative or it's concave down? Well, it's going to be, boom, at point C, we are going to say that that is creating a maximum point. So it's really cool for quickly finding these extrema, these max and min points. So that's what this whole thing says here. Does it always have to create something? No, but you can get some special cases. Remember, we just said, what if I have something like this? This would be that point of inflection. So when I look at this, yeah, the slope at C is 0, but is it causing a max or min? No, why not? Because what is the derivative at C? It actually is 0. So it doesn't always work. If I run into this example over here, I'm going to have to go back to the first derivative test and kind of see what's going on from the left and right side. Awesome. Let's use it. Let's go and put this in action. We're only going to do 2 problems. The thing is, sometimes it can take a while. So let's do the first one here. If I want to use a second derivative test to find it, so really I got to get in the habit, I need to find these critical points. So find the critical points. So first thing I do is find the derivative. So let's find the derivative of this bad boy here. I almost said derivatate. I'm not sure we can derivatate. We're going to go ahead and take this, and what are we going to do? We're going to set it equal to 0. So I'm going to go ahead and factor out a 4x on this, and what do we get? We get x squared minus 1. So when is this going to happen? It looks like if I solve both of these, this factors again, doesn't it? This will be x plus 1, x minus 1. So my critical points are going to happen when x equals 0, negative 1, and 1. So here are my critical points. So we're still going to find those critical points. Those are some exciting things going on here. And if we're talking second derivative, I'm going to go ahead and just find my points of inflection. So how am I going to do that? I'm going to look at the second derivative. So if I take the derivative of the derivative, I'm actually going to get 12x squared minus 4. And what's going to happen when I set that equal to 0? So I'm looking for points of inflection now. 0 equals, can I take a 4 out of this one? I'm going to take a 4 out, and I'm left with 3x squared minus 1. So if I solve this bad boy, when does this happen? This happens when 4 will never be 0. When does this equal 0? Well, you got to solve it. That's our whole thing. We're going to say, I'll put it down here so we can see it. We're saying when does this parentheses equal 0? We'll add 1 to both sides and then divide by 3. Ooh, so we're looking at, this is not so friendly, square root of both sides. We're looking at plus or minus the square root of 1 over 3. If I clean that up, the square root of the top is just 1, square root of the bottom is just that. And can I get rid of the radical on the bottom? Sure, I'll do times it by radical 3 on top and bottom. We get this bad boy. So we got, if you clean it up, you're really going to get that. Probably okay to leave it like this if you want, but that makes me happier there. We're going to get it all the way down. So this is going to be plus or minus radical 3 over 3. And what are these? These are the points of inflection right here. So some important information here. So if it ever asks you to find the point of inflections, second derivative, set equals 0. Critical points, guess what? They're critical. We need them to do a lot of these problems. So the goal was to look at the relative extrema, and then I'm going to come down here and look at this chart down here. So if I'm just finding the relative extrema, well, what am I doing? Let's use the derivative test. So this is where the slope is 0, or in some cases does not exist. And what do I need to do? I need to check the concavity. So really what I need to do is I need to check the second derivative of 0. So what is the second derivative of 0? We'll plug it in there. You're going to say 12 times 0 squared minus 4. The second derivative of 0, and again, all I really care about is the sign. This will be 12 times 0 is 0 minus 4. It's a negative 4. So what's going on here? Okay, sometimes I got to draw a picture to help me out here. The second derivative is negative, so what does that mean? That means it is concave down. If it's concave down, what does it tell me about 0? 0 is going to be a maximum point. Holy cow. So if I had to formally write this up, I'd write something like, because the second derivative is negative, and the critical point is 0, I can say that is a relative maximum because of the second derivative test. Holy cow, that's intense. How about the next one? Let's check negative 1. So if I do the second derivative of negative 1, I'm going to put it all the way into this bad boy over here. So I'm going to say 12 times negative 1 square it minus 4. And then again, I'm really most concerned about positive or negative. So that's going to be positive, isn't it? Negative 1 squared, 12 minus 4, 8. So what is this? Draw a little picture if it helps you out. Because it's positive, it's concave up. And because it's concave up, that means this must be a minimum point, a relative minimum point. Holy cow, this is awesome. So it's really quick, isn't it? I don't have to look at this from the left, it's increasing, from the right, it's decreasing. I'm just plugging and chugging, and I'm getting some good answers here. So let's wrap it up with, if I put 1 into the second derivative, so it'll be 12 times that 1 squared. This looks like it's going to be positive as well. You actually get the same thing, don't you? So this bad boy, boom, it's concave up. Because it's concave up, this is going to be a minimum point. That is awesome. That is super cool. So we quickly just labeled those 3 things as max or minimums. Again, if I was going to justify, you'd really have to write this out. Because of the second derivative being negative, concave, or by the second derivative test, it's these max or mins. Awesome. What if I just was more interested in concavity? So maybe I'm only interested in, where's this thing concave up or concave down? Well, now I'm going to make a little chart like we did before. So this chart's going to be based around my points of inflection. So that's where it's changing. So basically, from what? We have from negative infinity to radical 3 over 3 is one interval. Then I'm going to go from, oops, forgot the negative, from negative radical 3 over 3 to radical 3 over 3. And then I'm going to go from radical 3 over 3 all the way out to infinity. So I'm going to check those points of inflection. I'm going to come down here and get some test values. So what's an easy point? Well, negative radical 3 over 3 is going to be less than 1, because square root of 3 is 1 point blah blah blah. Divided by 3, it's going to be less than 1. So an easy point, negative 1. If you're not sure, you can do negative 2 if you like. I know 0 is a great point in between these two. And then I'm going to use 1 over here. So I've tried to pick some easy points. And in fact, look at the points I just picked. Those are awesome. Well played, Mr. Brust. Every now and then it all comes together. Check it out. Those are the critical points, aren't they? So I know the values. I just did all the work over here, so that's great. I know that the second derivative of negative 1 is positive. And I proved it. Oops. I can't say it's greater than positive. That's weird. Let's say that is greater than 0. So I know it's positive. I know the second derivative of 0, let's go ahead and write the number. The second derivative of 0 is negative 4, and the second derivative of, oops, what did I say, negative 4? The second derivative of 1 was positive 8. So because that's positive, I can conclude that this is concave up. I can conclude because that's negative, this is concave down. And I can conclude that this is concave up. So this is a great way to prove concavity, to justify it, but you got to show it all. The test value, the derivative, come up with the conclusion. You're concluding because this is positive, it's concave up. Awesome. So back in the day, back when I took calculus, you had to curve sketch them. So we're more interested in identifying because calculators are so nice today. But if I had to sketch this curve, we could do it pretty easily. Now, if you think about, we've got these max min points, we've got concavity, we've got points of inflection. I could quickly find an easy point to find would be when x is 0. Like if I had to go back to my function, why is the f of 0 so easy to find? Because you put 0 and you get 0 out. So if I'm guessing that 0 makes 0 and it is a critical point, which is a maximum, negative 1, I'm just going to guess it's here. I could put them in, but I think it's going to cross here and here. Alright, so if I draw these in, I know that I'm concave up somewhere in here until radical 3 over 3, and then it changes concavity. So I'm guessing roughly it looks like this. Does that have every piece I need? It looks like there's something going on here at radical 3 over 3, and negative radical 3 over 3, and radical 3 over 3. Not sure exactly where they are, but they're somewhere in there. And what's happening, does that make sense? Sure. I'm concave up, boom, till here, and then check it out, it's concave down from this little interval here. So you've got concave up, concave down, concave up. I can clearly see my points of inflection. It's changing concavity. Boom, I am good to go. That is awesome. So that's curve sketching with it. Second derivative test. Can we tie it all together for some particle motion? So this is going to be awesome. This is my favorite kind of problem here. So all kinds of good stuff. So we're going to find the velocity and the acceleration of this bad boy and see if we can get the motion going on one monster table. Ooh, I love it. So first, let's find the velocity. So if I look at the first derivative of this particle on the x-axis, the first derivative will be what? That should just turn into t squared minus 8t, and then plus 12. So there's the first derivative. The other information I'm going to need is I'm going to need the second derivative. I'm going to put the second derivative over here. So here's the acceleration, and what is the derivative of that? It looks like it's going to be 2t minus 8. So let's find some critical points. So the critical points will be over here. Let's set the velocity equal to 0. And now when we're talking motion, it's pretty cool because we're talking about this is when the velocity is 0. So when I actually have no velocity, I'm not moving. So let's factor this bad. I hope it factors. What gives me 12 and 8? I'm thinking 6 and 2. So these look like the factored. So when I solve this, I have a critical point at time equals 6 and at 2. So these are my critical points. Huge. This is when the velocity is stopping. All right. How about over here? Let's come over here and solve the acceleration. When does the particle have no acceleration? If I solve this, just bring your 8 over, and we're looking at t equals 4. So this is going to be my point of inflection. Maybe I should label this. So it looks like a possible point of inflection. We've got some critical points here, maybe some max and mins. And what I'd like to do in this case is make one huge table. A lot of times we have two separate tables, one for the first derivative, one for the second. I'm going to throw it all together here so I can get a good idea of what's going on. So how can I do this? So basically I got to hit all these critical numbers here and see what I get. So I'm going to look at all numbers in my interval. Let's see, give myself some room. I'm going to look at all numbers less than 2. So usually these particle motions, I should have wrote it, it's when time is greater than 0. So let's just start with 0. So I'm going to say, okay, from 0 until 2, I've got an interval of something going on. Then at 2, something exciting is going on. Then I'm looking at, and I should make these bigger. Then from what, 2 to 4, there's something going on. Then at the 4, we've got something going on. And from the interval 4 to 6, and at 6 we got something that's a critical point, and then from 6 on, so when t is greater than 6. Holy cow, this is a big table. So this is my intervals up top. I'm going to want to compare the first derivative. Oops, we're not doing x though. How about the first derivative with respect to time? And I want to look at the second derivative here. So I'm going to kind of look at everything here. All right, so we're going to look at all these different things and kind of find out what's going on with the shape of the graph, which will tell me what's going on with the motion of the particle. Oh, I love it. I love it. These are so good. So first things first, if I'm looking at the first derivative of these critical points, remember the whole point was the slope of the tangent line is 0. So I know at 2, the slope of the tangent line is 0. I know at 4, the slope of the tangent, not 4, whoa, how about 6? All right, so I know the slope of the tangent line is 0. Then I also found the second derivative when t is 4. The second derivative is 0. So here's some things I automatically know from my work above. So if I want to find out what's going on with the first derivative, let's pick a point between 0 and 2, maybe 1. Let's pick 1 and put it in there. If I do the f of 1, so if I say the f prime of 1 is what? I'm going to get, if I put 1 in this derivative, I get 1 minus 8 plus 12. It's a positive number. In fact, it's 5, so if we want to write it out. So what happens here? Then I know that this is an increasing function. Remember back to the other one, this is increasing, or in particle motion, it's moving right. Awesome. Let's do the f prime of 3. If I put 3 into this function, so into the derivative, I'm going to get 3 squared, which is 9, minus 24, plus 12. What's going to go on there? I think so. When I put that in, I get a negative 3. And what does that mean? It's a decreasing function over this interval, so it's going down, or in particle motion, it is going left. Awesome. How about when I plug 4 into the derivative? What's happening at that moment? So I'm going to get 16 minus 32. It's still going to be a negative, so it's still going left, so I'm just going to fill that in. The f prime of 4, if you want to put it, is a negative number. What was it? It's a negative number. I'm running out of room there. So it was 16 minus 32 minus 4, I think. So it's a minus 4 in there. Sorry, that looks crazy in there. So it's still moving left. What's going on here from 4 to 6? So I'll pick 5. And if I put 5 in this bad boy, 25 minus 40 is a negative 15, so I still got negative when I had that 12, so I think negative 3. So again, it's still decreasing, and that makes sense. It's decreasing, so it's still moving left until it hits this point right here. Then what happens, I'm hoping, well, I'm going bold here, making sense go increase after this. Doesn't have to. But when it's greater than 0, I've got 36 minus 48 plus, oh, I can't pick, that way I just did, I can't talk. I just put 6 in there, I got 0. Well played, Mr. Bruss, that was awesome. Let's pick a point like 7. So if I put 7 in there, 7 squared is 49 minus 56 plus that 12, I think you get a positive 5 on that. And because it's positive, that's going to be an increasing function. And it's moving right. So we got a lot of information right there about the direction that it's moving. Can we go ahead and find its concavity, or what's going on in the second derivative? So if I do the same kind of thing, if I look at the second derivative, which is much easier to work with, but I'm going to use the same test point. So at 1, if I put 1 in here, 2 minus 8, boom, negative 6. So what does that mean? It means that it's concave down. So I know it's negative, it's concave down, but what's happening here when you're concaving down? Well, we're going to compare the signs here of the first derivative and the second derivative. So that's pretty awesome. How about if I just put plain old 2 in there? It's still negative, isn't it? So it's still negative, still concave down. Let's try the second derivative of what? 3 was our test point. So 2 times 3 is 6. I get a negative 2. So it's still concave down. This whole thing is concave down. Oops, I spelled concave wrong. Concave down. Then I hit this point of maybe a point of inflection. I gotta test it. It's not always, but let's see what happens here. So if I put in, what do we put, the 0.5 into my second derivative? So put 5 into this bad boy, I get 10 minus 8 is 2, so it's positive. So this is concave up. And you can put in 6, you're gonna still get a positive here. And then a number bigger than 6, I think we did 7. You get 14 minus 8 is 6, so it's still all concave up. And I probably should have wrote that out in there. I didn't have a ton of room in there. So you can see the general shape of it's going to be concave down from here, concave up from here. And again, excuse me, the important parts are when I go from concave down to concave up. So when I'm looking, I went from a negative to a positive right here. So this is definitely creating this point of inflection. So yes, that is you have to check it. So it's a possible point of inflection. Boom, it does work. What are some other important things here? I went from increasing to decreasing. I went from positive to negative. So when I see this thing right here, I've got these I've got these extrema. So what is 2? If I'm going from up to down, if I'm going from increasing to decreasing, yeah, 2 is going to be a maximum. Or that was the first derivative test. If I look at the second derivative test, look at this. At 2, it's concave down, so you can see it right there. Like, there's my concave down. It's a maximum point. So you got options now. This is crazy. Look at this chart. I love it. I love it. Where else is exciting? So if you do first derivative test, here's first derivative test. It's going from decreasing to increasing. So some people like to think about that. It's going from down to up, so that creates a minimum. Some people like to do the second derivative test. Boom. It's concave up, so yeah, it's going to be the minimum. So we've got it proved both ways. This chart does everything. So we just proved min, max, and that it's a point of inflection. Can you tell me about the speed? Can we wrap this thing up with some speed? So what's cool about this chart when I can combine them all together is if my signs are the same, then I'm speeding up. So if I'm increasing, I've got a positive, but I've got a negative, I'm actually slowing down right here. Isn't that crazy? Because my signs are different. So I'm actually slowing down because the first derivative is positive, second derivative is negative. At 0, I have no velocity, so I'm not even moving. Decreasing, check it out, negative, negative. So what's happening? The particle is actually speeding up. So this is huge for that whole slowing down, speeding up kind of thing. If the signs are the same, you're speeding up. If the signs are different, you're slowing down. So I've got a negative and a positive, so what am I doing? I'm slowing down on this interval. And I'm not moving because I have no velocity here. And then what's happening here? I've got increasing, positive, positive, so I'm speeding back up. Holy cow. That's why we're only doing 2 problems, because they take so long. So the particle really is slowing down from 0 to 2. It takes a little, then it speeds up from 2 to 4. Then from 4 to 6 it slows down, and everything above 6 is speeding up. So that just really thoroughly described the motion of this particle. That table is awesome. This is the type of stuff I like to leave around, maybe hang on my fridge at home, show how much work that I do at school, because it just looks pretty awesome. All right, excellent. That had everything. That was a great problem. We're going to wrap it up looking at some graphs. And in the practice, I'm going to have you look at a lot of tables, so I'm going to practice some of that too, but I think we've done enough tables that we should be okay. Let's check out this graph because this gets crazy. Remember, this is the derivative, so I'm going to give you the derivative, and I want to know about what the points of inflection and the intervals of concavity, so that whole concave up, concave down. So where do I get points of inflection? Well, remember, that's when the second derivative equals 0. Well, when does that happen? Here it is. Boom. So I'm looking at, there's a point. Careful, here's a point right here, and here's a point. So here are all the places where I could have a point of inflection. Do I have a point of inflection? We need to double check it. So tell me about the slope. Remember, this is the derivative, so I want the derivative of the derivative. So coming into this, I have a slope of the tangent line is negative. Then I have 0. Coming out of it, it's positive. So I'm going from the second derivative would be negative to a positive. So is that a point of inflection? Sure, this is concave down to concave up. Isn't that crazy? So yes, so -2 is a point of inflection. And in fact, that's where my concavity, so how am I going to write this? Let's do -2 is a point of inflection. So when x is -2, we got a point of inflection. Is 0 a point of inflection? So you can write down, this is a possible case. Is that a point of inflection? Well, the slope of the tangent line to the derivative, so the second derivative is positive. Well, check it out. It's positive, positive. It's still positive, isn't it? So you're going positive, this point positive. Does that create a point of inflection? No, that is not a point of inflection. How about up here? The slope of the tangent line is positive to a negative, so the second derivative is positive to a negative. So you're really going from concave up to concave down. So yes, we've got another point of inflection at 2, and maybe you recognize that there are going to be these max and min points right here. So can I talk about concavity? Sure, I can talk about concavity all day. It looks like from -infinity to -2, what's happening? We've got concave, it's down, so it's concave down, and from 2 on. So here are my 2 intervals where I am concave down. So it's weird because you're looking at the derivative of the derivative. So it's concave down. Where am I concave up? I'm actually concave up all the way from what? -2 all the way to +2. Maybe I should have separated these. I'm concave up. Awesome. Very nice. So again, it kind of hurts the brain. You got to slow down, think about it, draw a picture, tell me what's going on. Let's try with some pointy lines here. So remember, it's also true when the derivative doesn't exist. So here's a place where the derivative doesn't exist. So we have to be careful. We have to check all of these points. So let's write them down and maybe cross off the ones. I need to check -1. I need to check 1. And I really need to check 2. So are these points of inflection? Well, let's find out. So I'm going from the derivative is negative to the derivative is positive here. So I'm going from concave down to, it looks like, concave up. And so does that create a point of inflection? Yes, this is definitely a point of inflection. How about here? So I know that I'm positive from this side, and if I draw the slope of the tangent line, I'm negative from this side. So at this point 1, I'm changing from concave up to concave down. Yes, this is a point of inflection. How about this? The slope of the tangent line is negative here, and then it's actually positive. So what's going on here? I'm changing from a negative to a, hey, they're all points of inflection. So yes, they're all points of inflection here. They're all relative max or min. So really, it needs to happen at these max or min points. Do I want to talk concavity? I always want to talk concavity. So where am I? Let's try if I label this a little better. I've got concave down. Where am I concave down? Well, it looks like from -infinity to -1, I'm concave down. Also from 1 to 2, I am concave down. Where am I concave up? I am concave up from -1 to, is that 1? And it's from 2 until 3. Holy cow, I hope you can read my handwriting. That is it. So I just threw a ton of information out there. You got to practice these. If the practice is not enough, go do the corrective assignment. Practice these bad boys. Second derivative test. Love it. Good luck on the master check. Peace out.